Hey. Good to go? Start? Shall I start? Yes. I'll just start then, right? Okay. So morning everyone. We had some delays. We were locked out because it's carnival and we're studying. So yeah. Anyway, so we're gonna talk about restricted Boltzmann machines today. So wait, give me a minute. So yeah. So essentially, like you've all seen Bix's class, and the only thing that's different between RBMs and the Boltzmann machines is the restricted portion. We force the visible units and hidden units into two separate components which only interact with each other and not amongst themselves. So it's a bipartite graph, and that makes things easier. And why we do this is that you're going to see this later today. The math really works out. It's really neat, and it just makes things really simple. I'm going to get to that. And another motivation is that, so if you guys remember the VA's lecture and recitation, so we were talking about a latent distribution and the true and the production from that. So, but both of these were trained independently. There was no guarantee that they correspond to the same joint distribution, but here we can kind of force that because that's how we derive things. And mostly people use it for pre-training autoencoders because RBMs are good at finding representations. We're going to get to that as well. But you can also use it as feature extractors, and if you have missing data, you can. So if there's part of like an image missing, you can start off the net and let it generate complete the sample and do stuff like that. But primarily, it's used for pre-training autoencoders these days. So yeah, so this is so when we're talking about graphical models, so we want to come back to probabilities at some stage. So the way we do it is we first define an energy function and then come back from it towards probability. So the energy function that we choose for RBMs is of this form, where you have like a linear for both hidden and visible. Throughout this lecture, H will be hidden and V will be the visible nodes. And then there's a term with the W matrix where both of them interact with each other. So yeah, so if you look at this, so I've just expanded these out. So broadly, you want energy to be lowered, so that like that's the way you define things. That's why there's a negative. So if the bias, let's talk about the first term. If the bias A was positive, and the component A, if the bias term AI was positive, and the component VI was positive as well, this is positive, so there's a negative, so that reduces the energy, so that's good. That's what we want. So this is sort of the intuition that if AI is positive, it will prefer situations where VI is also positive, and vice versa. So we're going to get to that in more detail. There is like some similarity between the energy function that we use for Hopfield nets. So it was kind of, so we only had Y, and now we have two terms. So it's just, it's generalizing the same thing even further. So what do these nodes do? So let's say you have some visible units. This is where we put in our input data. So let's say we're talking about MNIST images, and let's say the first three things correspond to the first 3 pixels in the row. Usually they're all going to be black. So let's say if all of these pixels and some other like if some subset of the visible nodes have always got the same values, if they're always black or they're always white, So there's gonna, like, it makes sense for the network to have one hidden unit which is strongly correlated to this, so that the energy term reduces by a lot whenever these are positive. So so that's one thing. And so let's say like this second blue hidden thing is the correlation. Because we saw that AI and VI prefer to be in the same, like both of them are either positive or negative. So this is the correlation that this will have. And you also have bias terms, because if, let's say, in my MNIST images, the top left pixel is the only thing which is constant and it doesn't change the value at all. You don't want to directly dedicate a hidden node to store just that one pixel information. So you can kind of think of the bias term as encoding that um, as kind of like a hidden node which is always on. But instead of sticking it in the hidden layer, you stick it in the bias term, so that captures that information. And and you might also want something that, so if all the inputs are 0, all the inputs are off, the energy term will not, so it's all multiplicative, so everything, the terms will be 0, corresponding to the VIs. So in that case, you can rely on the biases of the hidden layer to ensure that those nodes are activated and the energy is still lowered further. So that's kind of the broad idea why you want biases, and what they do for the network. So yeah, so this is the standard. So we define an energy function, and to get back to a probability from that, we normalize it by the sum over all values. This is in general intractable because you're going to have to sum over all possible values for V and H, which is not really feasible. But if you are able to do that, then this term divided by Z corresponds to the actual probability of joint probability of V and H at that point. So so the cool part about RBMs is that we can, so given visible units, the hidden units are all independent of each other, and vice versa, which is not the case in normal Hopfield nets. So we're going to see how that makes the computation sort of feasible. So because if you have conditional independence, you can just sort of sample them and simply take the product of the terms. So because once you have the visible units available, did you check if the stream is working? So given the visible units, these are not interacting with each other at all. So they're all independent of each other, and so this is the sort of I'm not getting into the derivation. It's pretty straightforward. So Hugo La Rochelle has some. So he teaches this course somewhere, and he goes through the derivations where I think he actually does not make independence assumptions at the beginning, and then just assuming the form of energy that we had here, he's able to get to this. It's working? Yes. Okay. Cool. So yeah, so this is just this is what you get to for the probability if you step through the math. I'm not going to do that right now. We don't have enough time. But this corresponds to the actual sigmoid term, which is why we use sigmoids over here, and that's cool. So yeah. So let's talk about inference, where you want to calculate the probability of of a V, and you can do this by marginalizing it over H, and since it's a RBM, H can be capital H long vector of zeros and ones, and this is the energy term divided by normalization constant. So you can pull this out. This should have been transpose. You can pull this out, and you can split this summation into capital H individual summations where all H's are zeros and ones, and you calculate this. So like capital H times such summations. Now the cool thing about this is that H is binary. It's either 0 or 1. So if you stick it into this term, it's always going to be 1 plus x of this, which is the same as x of log of this. So using that, you can convert this to a sum. So this is the cool part. Like you had this h small h vector has an exponential. Has an exponential number of combinations, but but you're just able to get it down to a single linear summation. This is the really cool part, which makes it feasible. Like RBMs, Hopfield nets do not end up this clean. So this is the term that this is the expression that we got just putting A transpose back inside. So the objective of sorry.
Just kind of ask real quickly. Do we generally, when we initialize the hidden nodes, is that we initialize them as all zeros or random zeros and ones?
I guess if you were using the network as kind of like a pattern completion, you may want to you have some node data where you fill in, and otherwise if you're doing classification, just a few extra nodes that could also be seen as a pattern completion. But I guess otherwise you'll do something random.
Okay. So the overall objective, what we want to do is increase the probability of observing the actual training data, which is V. So as we discussed like a few slides back, that if AI is positive and VI is positive, then that's good for us because the energy reduces. So you want an alignment between the bias terms and the visible units, and you also want an alignment between the weights and the visible units. So that's kind of what we do over that, but like all of this is a lot of overhead for not like like expanding into this. So the first term So the first term is simple, like this must align with this. So you bias the probability of each input according to what you train this to be. And the second term has two components. So it's modeling dependencies between input elements. And so if you look at this, so this is kind of like a soft plus kind of thing. So is there a question? So this bias term controls the threshold. So this V transpose W term sort of indicates the alignment between the input and the weights, and the bias term sort of tells you where that how high this has to be before it's significant. So let's say we see that we set the bias as, let's say, somewhere over here. Then anything above this, so it's kind of like shifting the threshold of the soft plus. So that's kind of what you're doing. So yeah, this is telling how important it has to be, and this is telling how much it's correlated with our weights. So again, we want to increase PV. So we want to align W to find meaningful features, and we want to find biases which are able to get something meaningful out of this. So the training objective is standard, like negative log likelihood of the data. This should have been V. Using gradient descent. So this is the gradient with respect to the parameters theta, which includes weights and biases. So I'm not getting into the math again, but this corresponds to an expectation over small h of this term and an expectation over because you have to sum over both b and h, and the math that we have right now does not directly convert things down. So we use something called contrastive divergence. So the assumption is, so you have some initial input v, which is your training data. So we say that let's condition h on this training data, draw a sample, and call it h naught. And given this, we condition a v on this and draw another sample and call it v1. So this is kind of like a Monte Carlo, like you have this and then you go, like you zigzag, and the hope is that at infinity you're going to have some thing which converges and is a good representation of v. But again, you're not going to let things run to infinity. Typically, you run this for typically you just run it for k steps, and you call it contrastive divergence of k, CDK. And in general, it's observed that k, the k value of 1 is actually good enough. So that's nice. So why we are doing this is to approximate the gradients that we had in the previous slides, because we don't want to compute that intractable sum. So we wanted v and h terms. So we sample some v terms and v tilde and h tilde terms from using this method. So this was the original thing that we had. This sort of reduces to, so we assume this, and given this, we find h tilde. So this collapses down to this, and it's the same. So this we sample using the training data itself, which is this one, and this is actually sampled at v tilde. So what we are trying to do with this is that we have some energy. So let's say this is a state. It's one-dimensional on the slide, but let's imagine we're talking about MNIST input space. And this, let's say this is the energy graph, and let's say this is the probability graph, which share the axes, shares the state axis. And they're not exactly, but like there's an inverse relation between these two. So what we want is that given an input MNIST sample image, we want to bring that energy, the energy of that state down, so that the probability of that state goes up. But we want the neighborhood pixels which are not 7 to have higher energy, so that their probability is lower. So if you think about it in this term, so we input our MNIST 7 image over here, and then we want a situation where the neighborhood of that thing is, if there's any local minima in the neighborhood, it's pushed further up, because you don't want stuff like this to ever be present near your input data. So you push down anything which doesn't look like a digit itself. So this is not getting into the math derivation again, but so this is the update rules that these are the update rules for the parameters that you get from over there. And then do you want to present the?
Okay, sure.
Yeah.
Got the microphone, I guess.
Sorry. Yeah.
So where's the notebook? Do we just open it on GitHub, I guess? Oh, darn, I forgot to name it. What? Ooh. Oh, there it is. I think we should start with the code, not with the notebook, though. All right. Yeah, let's do this one.
Oh, I should put this up here. It's not.
Oh, yeah.
Just 1 second.
All right, so created a notebook just to like demonstrate how you might actually create these Hopfield networks, restricted Boltzmann machine and whatever in PyTorch. And so here's this, there's this Python file containing a bunch of models. The code is available online. We basically just posted it. If you want, you can look at it while we go through it. I'll be going through the code on the screen. First, okay, where's the mouse anyway?
So it's not a duplicate, so you're gonna have to.
Is the screen on the left or the right?
It's on the left.
Okay. Then, all right, so this implementation of Hopfield networks is gonna be a little bit strange compared to like other feed-forward networks or like other networks that you would make in PyTorch, because first of all, according to our derivations, we're kind of calculating the derivative directly. We're not calculating a loss and letting AutoGrad find the derivative. So I use some tricks to make AutoGrad actually compute that derivative for us, and then we just calculate the derivative, and then we do something so that AutoGrad finds that as the derivative. And also, if you think about it, like the way the whole forward-backward thing behaves very differently with Hopfield networks, because with a regular feed-forward network, you put data in, and then it's all like comes in one stream, and it shows up on the other side. With the Hopfield networks, there's this kind of like iterative process of, all right, let's update all the neurons and then do it again until some unspecified convergence criterion, or just n steps or something. And so the overall structure that I've done over here was basically we have, oh darn, I'm not used to it being on the right. Yeah? Zooming in, all right. Is it not Control plus? Oh, there's. Lag.
Yeah, it's being super slow. Stop. Yeah, it'll happen. It'll
Okay.
you
And
can
so.
click here if that makes things easier.
And so the overall approach that we have here is I've created several Hopfield networks, stochastic Hopfield network, and the whole family of these networks. And each of these has inherit from an abstract class, which have this kind of forward function, which takes in the values and a number of iterations. And then because like the way we compute our loss, we actually have to like interact with the network. We can't compute the loss just by having the output of the network. We actually have to like run the network a few times, or like manipulate the network otherwise. And so what I did is we have this kind of wrapper class, which I call it the training wrapper, which contains the network inside of it. So there's is it not showing there?
It's not a good drawing, so
Oh.
it doesn't stream.
Let's see, so there's an abstract class which contains pretty much all of the common logic for all of the models. I'll be going over them in detail really soon. But let's go to the wrappers, which are, okay, that's the Boltzmann machine. So we have these wrappers which contain the Hopfield network inside of it, which is kind of what happens here. And then when we just take in the values and we do everything that we need to finally compute a loss. Like in this case, we kind of do we compute one of the terms of the loss, and then we run the network on the input values, and we compute the other term of the loss, and then we calculate, and then we like combine them somehow. And so, any questions about like the overall approach before we start going kind of line by line?
So you're hijacking the forward definition to like do some additional things?
It's still a legal forward function. It's just like, it's a network that takes in values and outputs the loss directly instead of having a network and then a loss criterion. And it works by like having a network inside of it. That's like, it uses the network to compute the loss.
What does the abstract class mean?
I'll be going over it in detail, but it contains all of the common logic where, since the Hopfield network, the RBM all have very similar internal code at times. So it's like inheritance for object-oriented. All right, let's do this. So first we have, some utility functions. Since the Hopfield networks, when we talk about them, we basically use either positive one or negative one as the outputs. Like the math is much easier if you think of it like that. So you have the sign function instead of, let's compare if it's bigger than 0.5, or there's like, you wouldn't have to worry about factors of 2 or adding like biases to everything to get to 0.5 if you make all the outputs positive 1 and negative 1. And then there's another function over here which discretizes things. So if our original values have kind of real value inputs, we can set them to be the positive ones and negative ones, which we can do by, we compare against 0. This would give us basically a binary tensor. And for certain reasons, like PyTorch doesn't like it when you do operations between floats and binary tensors, so you turn this into a float. And then I do the rescale function, which moves everything from a 0 to 1 scale to negative 1 to 1 scale. And so some of these functions are for the stochastic networks, which I'll be getting into soon. And then we have this, the update function, which this function, what it does is, once you computed the fields for all of the neurons in a Hopfield network, it updates the values according to the fields. So like the simplest way to do it would be to just, you find the signs of all the fields and then you set the values to be equal to that. But then like, if you do this kind of synchronous update where everything kind of changes at the same time, you would often get into kind of cyclical behavior. So much of the theory makes sense when you only update like one neuron at a time. Although there are tricks to kind of like get around this. In this case, I actually did more than just one neuron at a time. So the way it works, first of all, I find the product of the values in the fields. So like, if you sum this up, it would be the energy. I have a function for that later, but when the product over here is negative, when the value in the field don't match in sign, then we're kind of like, we're allowed to flip it, basically. And so what I do here is I randomly generate, I make it so that for the ones that can flip, I have a 50% chance of actually flipping them. There's many implementations. You can also like just pick one of them and flip it, or you can make it a different probability. I found that like 0.5 worked pretty well. It's usually converged instead of doing the cyclical behavior. And so what you do is, this is the products less than 0 is going to be a binary tensor for which ones are going to be negative. And the random numbers is less than the flip probability is another binary tensor. And you can basically you can do a binary AND with it by multiplying the two. And then it's the same as before. We convert it to float and scale it to -1 to 1. And then we do a negative sign here because the ones that are eligible, we're multiplying by -1. And the other ones, we're multiplying by 1. And so in the end, we get the values. Some of them get flipped and some of them don't get flipped, according to whether their values match the field or not, and also with the 50% probability. Any questions about this? OK, and so here's the abstract network. First of all, it's inheriting from the module, so we can use that as like a module and anything else. Later, we'll be inheriting from the abstract looped network. And so first of all of the Hopfield networks, RBMs, they have kind of a number of units. So we're just having some common variable. There's also going to be like a set of weights, which we'll be using, but we're allowing the kind of like the classes that inherit from it to define what it is. Because like the way the weights work is very different for the Hopfield networks and RBMs and to the stochastic ones, I guess. So we're just like leaving them blank and letting the child implement that. The child being the class that inherits from this one. And so there's a function I have that initializes all the weights. And so if you think about it, for the Hopfield networks, there's certain constraints on this matrix of weights, because you're not like a neuron doesn't connect to itself, and also sometimes we want it to be symmetric. In this case, I actually forced the symmetric constraint. I do this by this kind of fixed weights function, which takes in the weights data, and it creates a kind of identity matrix with the same shape as the weight matrix. And let's see, I basically like average the weights with its transpose to make it symmetric, and then I took out the main diagonal. So the result is going to be a symmetric matrix with zeros along the main diagonal. So we can do that during the weight initialization phase, and then we'll have like a meaningful set of weights. And then there's some functions over here that are not implemented because we're letting the child class implement that. For example, things like compute the fields, which you can do very differently, and update everything, which may or may not use the update function from directly above. Then we can compute energy by using the compute fields, so we can just implement that for them, which since the fields is kind of the weight times the values, and so the energy is basically the values times the weight times the values times -1/2. It's the matrix formula that we've seen, the y transpose WY, basically. And so now for the kind of like the forward iteration functions. So this run iters is just the function that iterates several times over the Hopfield network's update rule. So we take in the values, and we compute the fields, and we do the update using them. And we do this several times, and we return that. And the forward function is just this running iterations. Now, for some of the stochastic ones, we actually have this separate inference stage where, if you think about it, when you run the network with kind of a more random stochastic network, then when you stop at any one point, that's kind of like only one sample of many different behaviors that the network could be having at the time. And so what we do is we run it forward to get to the point, like we run that many iterations first to kind of stabilize it. And then we sample the network's values several times, and we kind of take an average of that to basically find out what the average behavior of the network is after that amount of time. So like we run kind of a number of iterations just for inference, and for each one we're summing up the values, and we're dividing by the number of inference iterations. And in the end, we still want kind of +1, -1 output, so we discretize that. And so yeah, that's the entire kind of abstract network. Does anyone have questions about how this works? All right, so does the stream have anything? I don't think so. No. Okay. And so the Hopfield network is a really simple addition on top of that. The weights are just a kind of a parameter which contains basically a matrix of size num units by num units. We set that, like we establish that, and we initialize the weights immediately after. the way we compute the fields is we just matrix multiply the weights by the values with some bookkeeping to keep track of the kind of the dimensionality constraints that torch.matrix multiply forces us to have. So like we have to change this to have an extra batch dimension because they originally didn't. And we have to change this so that it's, for each batch, we have a two-dimensional vector of size like something by 1 by something, I think. Now this is something by 1. Like if we have n-dimensional inputs, we have to, and an n by n matrix, we have to multiply an n by n matrix by n by 1 vector. We can't just have a n vector for some reason. And then after that, we can like, we get rid of the extra dimension that we had to introduce to do matrix multiply. And then for update, we just use the update function that we had earlier. Now for the stochastic one, there's kind of this temperature variable, which is saying with a higher temperature, everything is very unstable and like the network is all around the place. And with a low temperature, going all the way down to 0, it behaves more and more deterministically. It becomes more similar to like a regular Hopfield network. And so the way the stochastic one works, first of all, we do something really similar by establishing its weights, the temperature, initialize everything. And let's see. Did I do that right? Oh, yeah. The difference is over here where we still compute the fields the same way as before, but then like now when we update things, we kind of like, the implementation I had over here is to introduce noise into the fields so that sometimes the flipped didn't work the other way. And so we kind of use like a kind of similar trick with the gumbo noise and the softmax with the logits, where in this case, I'm doing the noise to make it look like we're sampling from a sigmoid distribution, where if originally we have like kind of 0.5 as the field, then with a deterministic network, we want the value to basically immediately turn to 1 for whichever neuron had a field of 0.5. But with the kind of stochastic one, we find sigmoid of 0.5, and that's the probability that it becomes a 1. So like sigmoids of very positive numbers is very close to 1, will almost definitely turn into a 1. And a sigmoid of a very negative number, it's going to be like very close to 0. We're almost definitely not turning into 1. We're basically going to turn it into a negative 1 instead. And so the way the noisy fields function worked is basically we just generate gumbo noise, and we like add some of it, we subtract some of it, and we multiply by temperature to get to and add that to the fields. So with a really high temperature, this noise is really big, and so you would have like the behavior of the network will be kind of really random. Whereas with a temperature of 0, you see that it's basically just giving you the fields directly, and so it behaves exactly the same as a regular Hopfield network. And so, any questions about kind of how the stochastic version works? All right, and so this is the Boltzmann machine, the generic Boltzmann machine. So the kind of the most complicated model of them all. So we have like not only a number of units, we also have some of the hidden units. We have the temperature because it is stochastic, and then we also have like a number of iterations to set up the hidden state for a certain let's see, where did I use it again? We set up the hidden state, I think, when we go num samples. Yeah, this is kind of something useful when we're trying to deduce hidden values from visible values. And so the way the forward function works is the same. We just have a larger weight matrix, one that contains number of units and number of hidden units squared. And so like we pass in a vector of size num units plus number of hidden units, and then we multiply by this matrix to get another vector of that. So this function still works the same. For the update, where we do the same update in general as the stochastic network, but then I also include this extra parameter for whether or not we want to update the visible values, because sometimes, like when we're using the Boltzmann machine, we're actually trying to only calculate the hidden units and leave the visible ones completely untouched. And so in that case, we can just call this function and say like include visible is false, and then it'll only update the hidden units. So that's mainly useful when we're doing this function called expand data, which is where we're given only the hidden vectors, and we're trying to expand everything so that we have some values for we're only given the visible values, and we're doing things to kind of infer possible values for the hidden values. And so first of all, we're given the input visible values, and then we have a number of samples for each one, because the Hopfield network, the Boltzmann machine, can end up in many different hidden states for the same visible state. What we implement here is, given this is some bookkeeping where we create a tensor that contains the visible values and the tensor that contains the hidden values, which for now are not initialized. And we're gonna basically accumulate a bunch of samples and concatenate them at the end. What we do is for each time we want to generate a sample, we create a random initial state for our hidden values. We can do this by basically calling this uniform function, which generates uniform random data. We do rescale to get it to -1 and 1, discretize that, fill that in. This copy function is what you do to write to a tensor instead of, so if you just do like hidden vals.data equals something, then you're replacing the tensor entirely, where in this case, you're actually writing the values and like keeping the same tensor as before. And so, we're basically combining the visible values and the hidden values together into a single vector. And we do the update. We like compute the fields and update things and so on. We do this for a number of iterations to kind of like get the hidden state to converge somewhere. And like after that, we would have a reasonable candidate for what the hidden vectors can be. We append that to the list of things, and we concatenate that at the end. And so like you can see that this is a really slow process. If we have like 10 samples and we want to do like 1,000 iterations, then we just have to do all that just to create training data in the first place. We haven't even gotten to the regular forward pass until we can't even do the regular forward pass until we have like values for this hidden state. But that's why we have something called like the restricted Boltzmann machine, which basically it has, first of all, it has much fewer parameters. It just has the units and the number of normal units, the number of hidden units, and the temperature. We can initialize the weights, which in this case is just the weight matrix is no longer a square thing. It's only going from the number of visible units to the number of hidden units. It's kind of reflecting how in a restricted Boltzmann machine, where only the hidden units don't talk to each other and the visible units don't talk to each other. We just have the visible units interact with the hidden units, and the hidden units interact with the visible units. And so like that makes the computing fields a bit different. We compute if you remember the diagram that Rajat showed about how we computed how we do forward iterations with the restricted Boltzmann machine, we kind of like, we compute the hidden values from the visible values, and then we compute the visible values from the hidden values, and we do this on and on. And so in this case, basically, we just given both the hidden and the visible values, we compute a new hidden value from the visible values, and we compute new visible values from the hidden values with a lot of boilerplate about having to do a matrix multiply. And then in the end, we concatenate those together. We run this compute fields many times to do this like constant process of visible from hidden, hidden from visible, and so on. And yeah, the update works the same as the other stochastic networks. And the expand data no longer has all of the looping and the number of samples or anything, because for any given visible data, you can just directly create the hidden data. If you do it twice, you get the same value both times. So which is why you can just find the hidden values by doing this update once, which is what I did here. I did an update, and then I fixed the visible ones to be the ones that you've seen earlier, and we returned that. And now these wrapper functions are used to actually train everything, where for the Hopfield network, we do the kind of the training process where we're moving from the training data a few steps around it to kind of like get into the neighborhood, and we're trying to like discourage the network from outputting something in the neighborhood while creating like a bowl around the true values that you found. And so you can do this by, first of all, there's the term that, the kind of positive term I call it, the term that the network should be trying to, for like, this is, the bigger this term is, the better, where we're making the weights approximates the visible values times its transpose, which is kind of what we do with Hebbian learning. And then we're also creating this kind of set of evolved values, which is we take in the initial values and we move it a few steps, so we end up somewhere in the bowl, like somewhere in the neighborhood, and we try to pull that one upward. So we're pulling downward the values we want, and we're pulling upward the values around the values we want. So in the end, we end up with this like little bowl around all of the training values that we want to see. And the way we kind of like hack the AutoGrad to work with this is, first of all, we've already computed this kind of, this is what we want our gradients to be, but then this function is supposed to return a loss, and AutoGrad is supposed to find the gradients. So you can just multiply the weights directly by it and sum everything. And I divided by something just so that the losses look like reasonable values. And so when you do this, when you take the derivative of an arbitrary weight value, then you'll just get you get back the value in this gradient matrix. So AutoGrad would immediately find this value that we wanted. And this is just like a little bit of a precaution when the kind of like, when the network evolves somewhere that's really far away somehow because all the weights are huge, or it's not very close anywhere to convergence, then I just kind of cancel that update step by giving you kind of a constant value, which is 0. And otherwise, we use that and let the AutoGrad take care of the update. With all the other ones, it's pretty similar. Note that for the stochastic ones, though, we don't do this. I think we more or less just sample randomly from the whole space of values and compare that with the training values, instead of actually doing the contrastive divergence thing that we've mentioned in the previous Hopfield network training wrapper. So like we basically generate a bunch of random values, and then we like run the network on those, and that gets factored into the term of what we don't want to see from the network. And so we're still creating a bowl. We're just like pulling everything up kind of uniformly and pulling down the training values that we want to see from the network. And yeah, the rest looks pretty similar. With Boltzmann machine, it's just, yeah, it's also similar to the other stochastic version. With the restricted Boltzmann machine, it's pretty common to do the contrastive divergence thing again. So once again, I have like the values, we evolve them a few times, and we pull down the neighborhood. We pull down the true values, and we pull up the neighborhood, and so on. And then in the end, we do the hack again. That should be how it works over here. Let's see if I can pull up the IPython notebook. It's pretty short though, so basically, does it show up there? No, it doesn't. Right. There. And so basically, I import everything that I need, and I create an MNIST data set. Over here, we say, like I'm saying that I only want the first 2,000, even though the data set has like 60,000 things. Because the way a Hopfield network works, it's not really a generalization tool so much as like a memorization tool. So if you tell the Hopfield network or RBM to memorize too many things, then it could actually get quite confused. In here, I just told it to memorize the first 2,000 MNIST digits, which if you think about it, the MNIST only has dimensionality of like 700 and something. So it actually can't perfectly store all of those values, but it's still, I think it still handled 2000 fairly well. And so like the way the data works over here is, first of all, I discretize the digit that shows up inside as the input, and also included 10 extra dimensions that show you like which label it is. So I'm using this network actually to do some classification just to see what it'll do for the lols. And so in this case, this is an example input where it's just the first digit. It's a 5, and the last 10 dimensions is a one-hot representation of 5, which I show over here. And so I create the network, and then I train it. It trains pretty quickly. So the trainer over here is just the wrapper that goes around the network. So we can use the wrapper to train the thing, and then we can use the network to do all of our demos after. So for instance, in here, we create an example mnist digit from the remaining digits between 2000 and 60,000. Because if you pick the ones within the first 2000, it actually basically looks the same as your input. If you try to memorize more things, then it becomes more different. Though with 2000, it worked pretty well. And so what I do here is I've cleared out the data, the one-hot representation of the label, because I'm going to see whether the network can actually classify an arbitrary input. And I run the network through that example input to see what it evolved into after 1,000 iterations. So the original data looked like, the original data looked like this, which is, it shows a 0 here because we kind of blinked out all of the label data. And so it only sees the 7, and it can't rely on this. And it basically does kind of pattern completion on top of this, where the kind of incomplete part is the one-hot 10-dimensional vector at the end. So after pattern completion, we end up with a really similar 7, maybe with a few dots changed in somewhere. And then we actually filled in the one-hot vector to say that this was a 7. And so this network does classification. Wait, why is it? So this was a partial experiment I was doing on the Boltzmann machine, which I think it didn't quite work with this one experiment. I got some coding error wrong, but this is an outdated network. Let's see if what did it actually do at the end though? Oh, it didn't run it, whatever. But the idea is you can also create a restricted Boltzmann machine, and you train it in much the same way. And then now you can access the weights of that Boltzmann machine directly to you replace a different traditional feed-forward network or something with those weights. And in this way, you kind of pre-train your network. And so that's how you can use these networks to pre-train things instead of just doing random initialization with Xavier or something and hoping that it finds something useful. And so is there any questions about how this works? Because that's the end of the notebook. Yeah, it looks different on your side. But I mean, this is what it should look like. But it's not that different. It's just it has a few extra lines for when I was running experiments. Does anyone have questions about how this works? Or I guess that's about it then. Yeah.
How long did it take to train the RBM?
Well, this one is mnist, so it runs really quickly. Just a few minutes was. I just only need to train a few minutes for the one demo over there. And I think these losses actually mean something because even though we basically just did it as a hack to get the gradients we wanted, they all seem to be positive, and it's kind of interesting. When it goes negative, I think it's basically saying that the contrastive divergence is doing something really weird. After a few iterations, it's jumped all the way to a different valley. And when the moment you see negative values, it's something bad is happening. That's a lot of outputs. Okay. Let's see. So how do you use the RBMs to pre-train things that aren't the vanilla feed forward?
So the issue, sorry. So the issue with training autoencoders is that if the input data dimensionality is too high, um, and on top of that you have multiple layers. So let's take a concrete example. Let's talk about MNIST, and you're going from 784 to, let's say, you want a representation in a lower dimension, let's say 100. So autoencoders starting at a random initialization are not easy to train, like we don't have a demo for that, but it really makes a difference if you start off at a good initialization. So the claim that that we make is that RBMs are able to capture the features in the data itself. So let me pull up. Wait. Do you want to search for that RBM filters, like MNIST RBM filters? The claim was, if you go back to the beginning of the recitation, that you have some weights so you have weights and biases. The training objective makes them correlated with the inputs. So if you have some inputs which are always the same, you have the biases. You have a corresponding unit in the hidden layer which switches on when they're all on and switches off when they're all off, and similar things for biases. So yeah, something like this. So if you actually visualize, do you see? Yeah. So if you so if you actually visualize the hidden layer filters that it learns for MNIST, so you get these kind of things, and you see that these filters do correspond to meaningful things that you would expect from the data. And
yeah, if you ever looked at filters from like a vanilla feed-forward network, you see that's kind of the patterns that it learns don't look like digits. They kind of look like a smush of like 5 digits together or something.
Yeah.
So these actually look like different individual digits.
Yeah. So this is just a good initialization to begin your autoencoder with, but the drawback is that RBMs are stacking RBMs is really difficult. Like the math that we use to make everything simple and tractable with one hidden layer, if you try to do it twice, you have to do like a forward and a backward thing, so the computation doesn't work out. It's really slow to train more than one hidden layer for RBMs. So if you want if you want to train an autoencoder which has more than one hidden unit, so either you have successive RBM trainings, so like for example, you go from MNIST 784 to, let's say, 400. That's one RBM, and then you use those weights as initializations. And then from 300, you want to go to 100. So you use this data and you train another RBM. So it kind of gets messy, but it's still, it helps enough that people still do it. Because as you see, like it's good weights to start off with, and then, yeah. So, because as Jerry said, RBMs are they end up being more of a memory thing rather than a generalization thing. Additionally, VAEs, so what I'm trying to say is that instead of RBMs, people are sort of focusing on VAEs right now, and RBMs are not really used. The math is really cool, but that's pretty much it. VAEs are easier to train because you can just have end-to-end things. You don't have to do successive layer-by-layer additions or computations, and it's a generative model as opposed to memory. So
yeah, like this could be pretty useful as like a content addressable memory.
Yeah.
If you look at the papers about kind of given half of a face, finish the other half of the face.
Yeah. Yeah, RBMs are useful. So if you have noisy data,
so you can sort of, and if you have a clean data set of the same images, so you can train an RBM and use it to complete the noisy data, because you assume, so you claim that the noise is different initialization and then you let it run. So yeah, I mean, there are applications. It's cool mathematically. But mostly it's just used for pre-training autoencoders for now. Yeah.
Yeah.
What if your input is a mix of real and, say, categorical variables that have been more hot-coded?
A mix of real and categorical. So like, I think for real values, you the only way to deal with them is like you sample them, or
Yeah,
like
so.
you pretend it's a distribution or something.
I think they assume the normal. Yeah, I'm not too sure myself, but they do assume that the data, the each, yeah. So, but yeah.
Like if you kind of relax the whole structure and you allow it to like take intermediate values between 1 and -1, then like the whole structure breaks down and you're basically just finding the one minimum of a quadratic, which is, you can do this much easier than using an RBM.
Yeah.
And it's also often not that interesting. It's kind of like an average of everything.
The fact that it's binary makes the exponential sum into a linear sum, because you can just do that. So if you remove that constraint, like things just break. So yeah. So yeah, any further?
That's the one I made over there didn't have biases, but that's a pretty easy fix if you just have an input value that's just always 1 or something.
That's left as an exercise.
Yeah, I think nothing else.
That it?
Yeah, cool.
Cool. So yeah, that's it.